So thanks, Sean. Thanks for having me again. I should note at the beginning this was originally prepared as a public lecture, which I didn't end up giving because I was sick, but that explains why it will be fairly general and not very technical. I've added a few slides, obviously, to adjust this to this audience, but we're not going to be getting into sequent calculi of linear logic or anything. Some of you may have heard an earlier talk I gave on similar subjects at 2016. I spoke at the AAL about linear logic and deep learning. Just wanted to sort of give a brief update on that since it's relevant to this talk. So if you want some mathematics which is related and sort of explains how I got interested in these topics, there's some joint work of myself with James, is he here? Yeah, so that's James, on differential linear logic. And the first link here is to a GitHub repository where you can see my attempts to make what was in that earlier talk in 2016 work. The experiments didn't end up being a success, but there's an implementation there of DeepMind's neural Turing machine in TensorFlow. So that's my sort of experience working with these objects. Okay, so as I said, so because of these projects, and particularly the first one, I've been paying attention to these areas over the last few years. And I think there's some interesting implications for mathematicians and logicians, and I'd like to share some of that with you today. So I'm going to start with a brief summary of the state of the art in artificial intelligence and machine learning. Okay, so then I'll go a bit further back and talk about some of the history of these ideas, and then the main part of the talk is in the third part. All right, so I want to explain briefly what I'm talking about. So a neural network is a particular kind of function from Rm to Rn. It's a parameterized function, so it's a function which depends on a vector of weights, which is denoted W here. So what's that got to do with the tasks that people typically get neural networks to do? Well, you encode the input data, in this case, cute cat, as a vector, a very high dimensional vector. And then the idea is that you would get the function to output well, in this case, a probability distribution over classification labels cat and dog, right, which tells you how certain the model is that the photo contains a cat. Right, and that probability distribution is a vector in R2, or Rn for some n. So the question is, of course, how you would produce a function fw which does the job well, that is, how you would find a good set of weights. And the answer, at least in the current approaches, typically is training. So you start with training data, a large set of training data. That's a set of pairs of inputs and outputs which are correct. And once you have a large set of such pairs, you can form an error function which tells you, well, given some randomly initialized weights, for instance w, how good your current function fw is at outputting yi given xi as an input for each I. And then the task is just to find a w which minimizes this error. That training process, the process of finding a w which makes your function f sub w good at whatever it is you're wanting it to do, is typically gradient descent. So you use calculus, you differentiate fw with respect to its weights, and then you move along some error surface to minimize the error. And that process, so this surface here is the graph of EW as a function of the weights, so the error at a given set of weights. So you randomly initialize the weights, that's some random point on that surface, and then you're trying to move downhill to find a set of weights which minimizes the error. Well, minimizes the error on your training data, right? And then the idea is that you then take that function fw with the same set of weights that you found and you apply it to examples which were not part of the training data. And when people say deep learning, they just mean machine learning using deep neural networks. So a deep neural network is that particular kind of function constructed in a particular way, which I'll describe now. And this process of gradient descent is what people mean by learning in this case. Okay, so how does one get this particular class of functions f sub w? These are roughly speaking differentiable. They're piecewise differentiable functions, but they're constructed in a very simple way. Let me describe a function which, given a list of scalar inputs, x1 through, well, xj all the way up to xm in the case I was describing earlier, and outputs another list of scalars y1 through, say, yn, just by matrix multiplication. Oriented edges between these nodes all acquire weights. Those are scalar values, and then you compute the next layer by multiplying the matrix, summing over j. That gives you the values, one value per node, and then you apply some nonlinear function, in this case sigma, which is just max x comma 0. You apply that to this linear function of the xj's, and that's the values of the yi's. So that tells you how to propagate, given some set of weights, values at one layer to values at the next layer. Well, you can imagine now several layers, right? So this is layer k, that's layer k plus 1. And if I can propagate values from one layer to the next, then I can just iterate this to propagate values from the input layer, which is the cat, all the way through to the output layer, which in the classification example I gave earlier would just have two nodes, right, because I'm outputting two numbers. All I'm doing to send those inputs to those outputs is just a bunch of operations of the form I described. You multiply by weight matrices to get from each layer to the next, and then you just chain those operations together. So that defines the function f sub w if you know all the weights in between the first and final layer. So that's not differentiable, strictly speaking, because sigma, as I wrote it, was not a differentiable function. That's okay, you just do it anyway. It works. There's also other differentiable choices of sigmas that people use. Then there's the question of how to initialize the weights. This is another tricky subject which people took decades to sort of figure out the clever way to initialize things. So this whole business is very delicate and sensitive to how you initialize the weights and what sigmas you choose and so on. But if you do it right, then you get systems that really work. It's quite amazing. But there's three main areas where there have been genuine breakthroughs in the last, really 6 years. Deep learning as a field took off really in about 2012. So that was at a NIPS conference where Kochevsky, Sutskever, and Hinton showed for the first time how to use a convolutional neural network, which is a sort of modified form of the deep neural net I presented, to classify images. So roughly speaking, what I showed you with the cat, right, but with more complicated images. So there was an image net competition where there was a training set of, I think, 15 million images which had been labeled by hand by humans over many years, 2.5 years it took them on Mechanical Turk, paying people to label 15 million images in 22,000 categories. And then they took that as training data and they ran this competition. In 2012 was the first time it was won, I believe, by a neural net, and that really kicked off people's interest in this field. I've given a bunch of links there if you want to investigate further. So these slides will be on my webpage. Maybe I should put that somewhere. So the primary area of success for these methods is computer vision. That's still true, right? So these methods are now very good at those kinds of tasks. Another area that's seen a lot of genuine progress is machine translation. So last year, Google published a paper where they showed how to use what are called recurrent neural networks, something like 500 lines of TensorFlow code. TensorFlow is Google's machine learning language, replaced 500,000 lines of handcrafted, old school style machine translation. That is now what you're running if you ever go to Google Translate and type in a sentence. It's actually using that neural net-based system. The other big area that has sort of seen a breakthrough is in Go. So in 2016, there was a tournament where DeepMind's AlphaGo system played Lee Sedol in Korea and defeated him. I'm sort of curious, how many people have read this book or are sort of aware of this book? Yeah, I think this is a very interesting book. This was a series of lectures that von Neumann prepared near the end of his life. I think I remember correctly that he didn't give the lectures because he became ill. It's a small book, but this is one of the first places where someone really thought hard about the science of how the brain worked, how it was known at that time in 1958. So von Neumann observed, what we all sort of know now, which is that the brain is massively parallel but slow, whereas our computers are serial but fast. But there are many other observations in this book, and this is one of them that I think is quite striking. So what he's talking about here is what became a debate within the field of artificial intelligence, which is the distinction between a connectionist approach and a symbolist approach. What he's referring to as the primary language of the central nervous system is, we now think something closer to what was in that diagram earlier, with connections between nodes and weights and this very large graph with sort of mysterious meanings of these connections. But somehow out of a very parallel system built on weights in that sense, some sort of neural network, there emerges a secondary layer which we refer to as language and mathematics. And of course, this is a standard discussion of how this arises. So von Neumann was thinking about that back in 1958. It became a big point of debate. So the word artificial intelligence was coined in 1956, I think, at a conference which was organized by Minsky, McCarthy, Shannon, and Rochester. And for the early years, the symbolist approach, that is to say, focusing on the secondary language, was dominant. So the symbolist approach to artificial intelligence is to look at logic, which is our way of trying to understand what humans do when they reason, and using that as a basis for building artificial reasoning systems. Right? That approach focuses then on mathematical logic, on things like Lisp, on expert systems, and so on. There's another vision which is more close to what von Neumann was referring to as the primary language of the neural network or the brain, which is more what Norbert Wiener was talking about. So Norbert Wiener was a brilliant mathematician. One could argue the founder of the modern approach to artificial intelligence, although often he's not described in that way. So his cybernetics was a sort of synthesis of, he proved many important theorems in real analysis in mathematics. So he was focusing on information theory, statistics, control theory, feedback as a method for having intelligent control of physical systems. And this is more where people have ended up since 2012. So since neural nets came back onto the scene and really started dominating, people now tend to think, the dominant approach to artificial intelligence is now closer to what is being described here as Wiener's approach. So I just want to briefly advertise Wiener's writings. So if you're curious about these topics and you want to read a deep thinker who's thought about the effects of AI and automation on society, I think there's no better reference than Wiener. So he's really a brilliant man and wrote very clearly about these topics, way back in the 1940s and early 1950s. So in this quote, he's referring to, the fact he's very aware that despite the fact he's talking about continuous feedback and so on, that very much what he has in mind is mathematical logic and Leibniz's program for mechanizing logic. Okay, so it sort of brings me to the end of the history segment. So I want to say something briefly about the different kinds of mathematics that shows up if you crack open a deep learning textbook. So deep learning is the sort of connectionist approach to artificial intelligence, right? It's based on highly parallel, sort of graph-like systems in the sense I described earlier. And the mathematics that goes into that is linear algebra. So linear algebra is, I described earlier, this matrix multiplication. That's linear algebra. Calculus. So if I'm doing gradient descent, I'm differentiating everything to work out how to move around in the space of weights to minimize the error. The symbolist approach, which is more in the line of McCarthy and Minsky and these guys, is more what you're familiar with in this audience, right? So mathematical logic, Boolean algebra, lambda calculus, derivatives of lambda calculus in the sense of Lisp and so on. Also in the symbolist camp, I would put inductive logic in the form of Bayesian probability, because Bayesian probability is sort of founded on the axioms of Boolean algebra of propositions. Right? So one very interesting thing that's happening in the last year or so is that, I mean, people have talked for a long time about desiring a synthesis of these two approaches to AI. So you can find a very interesting paper of Minsky where he talks about this. But what's happening in the last few years is because companies like Uber, Google, and Facebook are just pouring untold millions into this area, people have had a lot of resources to go ahead and try actual engineering experiments which integrate these different kinds of approaches. I would say they're sort of in an alpha state right now because it's actually not very clear how to integrate Bayesian probability with neural networks, for instance. These are very different kinds of things. You can look at these languages, Pyro, TensorFlow, and PyTorch, and recent developments just in the last few months actually have added native support for distributions to TensorFlow and PyTorch. So these are sort of natively differentiable programming languages in which you can write machine learning models. As I said earlier, so my forays into this area have been entirely in this language, TensorFlow. And there's a talk there by Tenenbaum, who's a researcher, describing some of this recent work, which I recommend. Okay, so that's a bit of a look at the history and some of the mathematics involved. So now I want to change gears entirely. For a while, this will have no apparent link to AI, but you may be able to spot fairly quickly the link to logic. So this is a very old story. So the I Ching is a foundational text in Chinese philosophy. It sort of gets a bad rap now because it's basically a tarot card system, which is a bit silly when you look at it from that point of view. But that is really underestimating it. So it has been very important over thousands of years in Chinese philosophy and shouldn't be taken lightly. So I'm going to explain briefly what the I Ching is and then tie it into the earlier story. Okay, so maybe the way to start is just to consider the simplest kind of oracle. So an oracle gives you a yes or no answer to any given question, right? Okay, a yes or no answer is a bit. Well, there's a bunch of bits, right? You can see them. There's solid lines and there's broken lines. Those are bits. Okay, so if I ask 3 questions and get 3 replies, I've got 3 bits of information, and those are the 8 possible ways of getting 3 2-bit answers, right? So those sets of 3 bits are referred to as trigrams or gua. Okay, and the idea of the I Ching is that it proposes to identify these trigrams as sort of like the atoms of meaning. Okay, so here are the meanings that get assigned according to the old texts to these trigrams. But one thing to note is that in different contexts, the gua have different meanings. So if you're talking about families, then they have various assignments and so on. So the second thing you can do with trigrams is to combine them together. So if you combine 2 trigrams, you get a hexagram. So this is a 6-bit figure. Now, of course, then you can combine the meanings from these slides and get sort of complicated ideas or more complicated ideas. Now, that would be sort of interesting as it is, but the thing that makes the I Ching actually quite fascinating from a modern point of view is that it kind of had dynamics in it. So there was a rewrite rule on these hexagrams. So there was a sense in which when you're generating these, and there's a whole sort of mystical method of generating these bits, right? You throw sticks on the ground and so on. And as part of that, you can also generate a given row or bit which is somehow active. And if you modify that bit by swapping it for its negation, you get a different hexagram. So in that way, you get 2 hexagrams and some transition between them. And the narrative that's built up around the I Ching as a system for sort of understanding processes in the natural world, which is what it was intended to do, is tied up in not only generating these hexagrams, but in the transitions between them. Okay. All right. So the idea that the Chinese philosophers had was that the I Ching was meant to be a kind of universal symbolic system for understanding the world. Right? So you'd map phenomena in the world. They would be shadows of these hexagrams, and then you would understand processes in the world by studying the transitions between the hexagrams, the relations between them. So that's the idea. I don't know if I put a reference on the slides, but this is all explained in great detail in Wilhelm's book and also in Joseph Needham's texts on the history of science in China. Okay, so the I Ching Book of Changes, was very important in Chinese philosophy, and we would say too important. People placed a lot of belief, intellectuals in China placed a lot of belief in this system. They weren't silly people, so they did, many great philosophers in China did very deep work. But this was definitely a kind of blind spot for Chinese thinkers. And you can see this is a kind of typical example. So Kangxi was a very wise man and usually written about as a great emperor in the Qing dynasty. And he and many other Chinese intellectuals were aware of what was happening in the West. They were aware of Western mathematics and astronomy, but they tended to look at it and find antecedents for it in the I Ching. Right? And this led them to sort of not pay attention to what was happening in the way they probably should have been. And they didn't really start paying serious attention, the elites in China, until military incursions by European powers sort of forced them to pay attention. So what you're supposed to take from this story is, well, A, it's kind of interesting, this symbolic rewrite system. I don't think we had anything analogous in Western philosophy at that point, 600 BC. Right? Of course, it's similar in some ways to Platonism, but this dynamic aspect is quite novel, I think. But the thing I want you to take from this, in addition to that, is that the I Ching was a sort of beloved system of thought, which nonetheless caused a blind spot for otherwise very smart people. And I want to just pose the question of whether we might have a similar blind spot. I think we agree we don't have precisely the same blind spot, right? We measure things, we make precise predictions. So we're pretty sure that we're not making precisely the same mistake that the Chinese philosophers were making. But could there perhaps be some other kind of mistake? Not in the underlying logic of mathematics, but maybe in the way we think about it, and the way we use it, and the way we sort of relate to it as a cultural artifact. Well, how would we know if we had such a blind spot? Right? You can't see it, obviously, that's the whole point. Well, you find out about a blind spot when you run into a brick wall, right? And reality just shoves your nose in the fact that you were missing something. And I think, to come back to the topic of the first part of the talk, that recent progress in AI is revealing, maybe more than one, blind spots of precisely this kind. Now, I noticed one in my own thinking, and that's what I'm going to talk about, but I think there's going to be many realizations of this kind over the coming years. So the one that I realized I'm going to explain by fast-forwarding from ancient China to 2016 in Seoul, Korea. So who watched these matches? Yeah, this was great. So this is Lee Sedol, 18-time World Go champion. He's playing, I don't know which precise match this is, against AlphaGo. So there were 5 matches in total against this deep reinforcement learning system. Lee Sedol won one of them. That sounds like I'm putting him down a bit, but actually it's a very inspiring story. I highly encourage. There's a movie on Netflix called AlphaGo. It's really makes you proud to be made of meat, I would say. Okay, but he did lose, and this was a big shock to the Go playing world. But I would say, in terms of its lasting impact, not as big of a shock as what happened last year. So in June 2017, an updated version of AlphaGo called AlphaGo 0 played a 3-game match against Kejie, shown here. This was in Wuzhen in China. Kejie is, I think at that time, the top-rated world top-rated player, child prodigy in Go, and he lost all 3 of the games to the updated version of AlphaGo. Okay, well, humans lost chess to machines a long time ago, so big deal, right? This was coming. Why is this such a surprise? Well, I think there is something fundamentally different about this second loss, the loss of Kejie to this updated version of AlphaGo. And this is from David Silver. So this is the bad guy in this story, I suppose. So he's the lead research scientist and expert in reinforcement learning at DeepMind, who sort of led the team which created AlphaGo and AlphaGo 0. And at the end of the AlphaGo 0 paper, you'll find this pithy paragraph. So he points out that it took us thousands of years to accumulate Go knowledge, which was distilled into patterns, proverbs, and books. AlphaGo 0, interestingly, I haven't said the distinction. So the updated version wasn't just like fixing bugs. Okay. So the reason it was fundamentally different was that the original AlphaGo was trained on 160,000 human games. So I described at the beginning of the talk how you create a neural network, right? You need training data. And you put in this training data and then you do gradient descent and you find a good neural net. So in the first version of AlphaGo, humans could tell ourselves this lovely narrative, and I did it, right? It was like, okay, we worked really hard for thousands of years to learn about Go, and then we've sort of passed the torch to our descendants. We took all this knowledge and it was like, here you go. Went beyond us, but it was starting from the stuff we gave it. Sort of we could feel good about ourselves, I think. Now at that time, it was sort of clear reading the paper that what they were going to do next. And indeed they did do that the next year. AlphaGo 0 uses 0 human training games. There is no human games in AlphaGo 0, just the rules. You put in the rules of Go and a very modest sort of observation about the symmetry under rotation and so on, and then that's it. Okay, so AlphaGo was trained on hundreds of thousands of human games. AlphaGo 0, well, where did it actually get its training from then? And it wasn't just randomly initialized, then it played very well. It played itself. So it played itself like, I don't know, some number of millions of times, right? So at the beginning, it was just very bad Go players playing very bad Go players, just randomly putting down stones. But then this population of Go players sort of improved together. And this is very difficult to get to work in a stable way and so on. So technically a very big achievement, but very easy to describe, right? This system, just built on the rules, played itself millions of times. And on the way, rediscovered, as Silver is pointing out, many of the basic strategies that humans had found, but had found others that we had never thought of before. We still don't really, I think, know exactly what it knows, right? We can only find out by playing it and losing and then seeing what it did. Okay, so I have to admit that after the Lee Sedol game, I myself subscribed to this very heartwarming narrative I described earlier, even though I knew it was probably not going to last. And the Kejie games left me a bit shaken, I have to say. And I, for a long time, couldn't figure out why. So it's not merely because the machines are better at Go now. That happened with chess a long time ago. It's sort of expected. I don't think it's a very big deal necessarily, right? And I can say that because I wasn't that upset about the Lee Sedol matches, right? And it's not only that it was based on not using human training games, human games to train either. So I thought about it some more, and now I want to tell you very briefly sort of what I figured out. And this is coming back to this blind spot. So the blind spot I think I discovered in myself, which was revealed by these matches and which has been sort of revealed to the Go players more directly, is the following. As was just observed here, it's sort of very interesting. Well, maybe one should also point out that AlphaGo 0 plays chess, and it plays other games as well. You just put in different rules, same system. It's not to say it's going to take over the world tomorrow. It's not. It can't even play imperfect information games, right? So it's very limited. But nonetheless, it's not specific to Go. So from the point of view of a logician or a mathematician, this is quite fascinating, right? So for the first time, really in history, we can just sort of sit down, write a list of rules, and then sort of just enumerate some gigantic universe of possible plays using those rules. That has not been possible before, right? It took thousands of years to enumerate consequences of even very simple rules, right? But we're moving into an era where that is no longer perhaps the dominant way of enumerating that territory. Just to make this analogy to territory more precise, so beginning with a system of rules for a game or axioms, we can of course theoretically imagine generating the set of all valid games or true propositions, even if we can't enumerate them in some sort of reasonable way. But here's the blind spot, I think. So psychologically, I think we tend to identify that territory with what we mean by the word Go or by the word mathematics. But the way we use those words, we actually mean human Go or human mathematics. And I don't mean like some very culturally dependent approach to mathematics, although maybe that's the case. But what I mean is, when we talk about mathematics, we're actually describing more of a map, because we don't sit students down in classes and just give them some formula in set theory, absent any story about how it came to be. We give them some narrative which starts from very basic principles, working up to more complicated concepts, all the way up to this very complicated statement in set theory. Human mathematics seems more to me as a practitioner like a map than it does like the territory. And there's a gap between these two things, which in the case of the Go players has been exposed as being very wide indeed. So Go players are no longer able to sort of just think about Go as being the thing they know, right? There's more to Go now than there is to human Go. Okay, so I think this is at its root what I found disturbing about AlphaGo 0. Well, supposing that's true, what are we going to do about it? So I don't want to leave the end of the talk on this very, somewhat depressing note. I think what to do about it is a question for each of us to think about in the coming decades. So I don't think a machine's going to beat me at being a mathematician anytime soon, but I'm not going to bet against it in my lifetime, let alone in the next 100 years. Right? This would be extremely complacent and arrogant, I think. The Go players thought exactly the same thing 2 days before Lee Sedol's matches. And so I think one has to be a little humble about what's coming down the pipe. So I want to finish by saying something about, this is a sort of representative of a whole class of papers that are coming out at the moment. So what is this? So this, well, first maybe I'll just flag one of the authors. So Fei-Fei Li was the lead researcher on the team that put together the ImageNet benchmark, which I talked about earlier. So the ImageNet benchmark was this competition, which in 2012, those three authors won and kicked off the deep learning sort of craze. She's now, I think, head of research at Google Cloud's division on AI. The ImageNet competition was just about saying what was in an image, right? There's a dog in the image, there's a cat in the image, there's a guy surfing in the image. Much harder than describing what's in an image is reasoning about the contents of an image. And of course, we do that very well, right? So this is sort of the next step beyond ImageNet. So this benchmark called CLEVER, I don't know what the acronym stands for. You're given an image, it's generated by some, game engine, I suppose. It generates objects of different shapes, different size, different texture, and in different positions. And then there's some huge corpus of such images, and then there's questions. Now, I have trouble answering this question. I don't know if you can read it, but it's kind of complicated. What number of tiny brown shiny things are to the right of the matte sphere that is on the left side of the tiny red object to the right of the small yellow object? Okay, but if you think it through, you'll figure out it's just Yeah, it's just this one. That's right, yeah, you can cheat. Humans can cheat on this question, but... Right, okay, so there's one. It's that shiny brown thing over there. Okay, so and there's various ways of approaching, so that's the benchmark. You're given these photos, you're given questions, and then you get a good score if you answer the questions correctly. But the idea is you have to reason about this image in order to answer the question. You have to recognize the different shapes, the different textures. That's computer vision. But then you also have to count, and you have to do other basic reasoning tasks. So the approach taken in this paper is to generate programs. So these are programs in a very simple language, but it's easy to imagine where this field goes, right? You're given some domain-specific language or some sort of handcrafted intuitionistic logic, and the system is generating programs or proofs in that logic in order to solve the problem you give it. There's the program. It's actually a tree. It's sort of written in a funny way. So each one of these terms has an arity. So if this had an arity, 2, then those 2 things would be on the next branch under it and so on. So you can sort of in your head imagine this tree where the nodes are sort of sub-programs that it's been given. So in this case, it's given a bunch of basic programs, and these basic programs are computer vision tasks, which it also has to learn how to do. So this is sort of learned end to end. Okay, so the neural net part of the system learns to generate these programs in order to answer the questions. And that's becoming a very common approach to these reasoning problems. And the reason that's good is, as I said at the beginning, it's hard to think about what the weights in a neural net mean. But it's much easier to understand programs, right? At least in principle. The idea of these systems is that the program is a kind of communication between the neural net, which is sort of inscrutable, and the humans. And we can reason about the programs, and we can hopefully prove things about the programs, and we can do the logic we're used to applied to these outputs from the neural net part of the system. And this is, I think, going forward, if progress in AI continues, this kind of interaction between neural net-based systems and humans via programs or sort of ad hoc intuitionistic logics is probably going to be one of the large areas of utility for people like me.